we are going to solve an example problem of economic load dispatch with considering the losses. So if you see this problem, take note on the problem. Solve for economic load dispatch of generation. Solve for economic load dispatch of generation for a total demand of 850 megawatt. For a total demand of 850 megawatt. The fuel cost function is given below. The fuel cost function is given below. That is 561 plus 7.92 P1. 561 plus 7.92 P1 plus 0.001562 P1 square. So next, the fuel cost function of second generating unit is 310 plus 7.85. 310 plus 7.85 plus 0.00194 P2 square. 310 plus 7.85 P2 plus 0.00194 P2 square. Next, the fuel cost function of unit number 3, that is generating unit 3, is 78 plus 7.97 P3. 78 plus 7.97 P3 plus 0.00482. 0.00482 P3 square. P3 square. Next, the PLoss. The PLoss for the equation that is also given. So it consists of the 3 generating units. Why? Because the losses, transmission losses, which combines all the generating units. Losses that is being happened in all the generating units. So in the losses, it is given like 3 generating units. 0.0003 P1 squared plus 0.0009 P2 square plus 0.00012 P3 square. Okay, this is the PLoss equation. So what is the total demand? 850 megawatt. So while given with the problem, always you should note down this fuel cost, that is F1 of P1, F2 of P2, F3 of P3. Okay, so if it is like H1 of P1, that is heat rate function, then the fuel cost also will be given. So here, like the fuel cost function is equal to heat rate function into that fuel cost of particular generating unit, fuel rate of particular generating unit. So that also you need to multiply. So always first don't blindly solve the problem. The first you have to see this, whether it is fuel cost function is given or heat rate characteristics is given. Sometimes differentiation itself will be given, that is df1 divided by dp1, df2 divided by dp2, df3 divided by dp3. Like that also will be given. Sometimes differentiation itself, that is first differentiation itself, will be given in the problem. So you have to very, very careful while solving the problem, while seeing the questions. So whether it is fuel cost function or heat rate function, as well as differentiation, the first differentiate with respect to fuel cost function or not. Like that, if you see, then you go for solving. So don't simply blindly solve the problem. It is very, very important. Okay, so here the PLoss also will be given. So what is the general formulation we have solved in the previous class? What is the general formulation? Yeah, general formulation, that is dFi divided by dPi is equal to lambda into 1 minus dou PLoss divided by dou Pi. Okay, so this is the this is the general formulation, that is dFi divided by dPi is equal to lambda into 1 minus dou PLoss divided by dou Pi. So we already derived this equation. Whereas for This is with considering the losses. Without considering the losses, what is the formulation? That is dfi divided by dpa is equal to lambda. So here losses also will be considered. So dfi divided by dpa is equal to lambda into 1 minus dou p loss divided by dou p I. So we have to solve this. So for solving this, what we are doing is, first we will differentiate the fuel cost function to that particular okay generating unit. That is dfi divided by dpa. That we are going to find out first. Next we are going to find out that is dou p. After that we are substituting. Why? Because for simplification, sometimes while differentiation, or if it is a lengthy equation, there is a chance for mistake. So that's why, to avoid that any confusion, mistakes, everything. So we are solving by using this method. Like first we are differentiating with respect to the first generating unit, second generating unit, third generating unit, like. So what we are doing is, first we are differentiating as usual, like we are differentiating and equating it to 0. Okay, sorry, we are differentiating with respect to the power generating unit 1, that is df1 divided by dp1. So like if you differentiate, you will get the answer like this. You'll get the answer. This term will this constant term will be neglecting. So this term, so p1 will becomes 1, and this into multiply by 2. So you will get differentiate with respect to p1 7.92 plus 0.00312 p1. Next, similarly, we are differentiating fuel cost function 2, that is this function, with respect to p2. So while differentiating, we are getting the answer like this: 7.85 plus 0.00388 p2. Next, differentiating the fuel cost function 3 with respect to p3, that is 7.97 plus 0.00964 p3. Next, what we are doing, we are differentiating dou p loss with respect to dou pi. Okay, dou p loss with respect to dou pi. So what we are doing is, I is equal to 1, 2, 3, because 3 generating units only given. 3 generating units only given. So what we are doing is, we are just differentiating this, that is dou p loss divided by dou p1. Okay, so while differentiating, you will get the answer like this. You will get the answer like this. Next, similarly, we are differentiating dou p loss with respect to dou p2. There also we are getting the like 0.001 HP2, dou p loss divided by dou p3, that is 0.00024 p3. Okay, so here what we are doing is, we are in this equation, that is dou p loss, we are differentiating and with respect to that particular generating unit. Dou p loss divided by dou p1, dou p loss divided by dou p2, dou p loss divided by dou p3. Like that we are differentiating. After that, what is the general formulation? After finding out all these things, what is the general formulation here? The general formulation divided by dpi is equal to lambda into 1 minus dou p loss divided by dou pi. Okay, this is the general formulation. This already we found out. This also we already found. So the thing is that I. So I means three generating units. 1, 2, 3, like that. For 3 equation it will come. So simply like that, substituting whatever we had differentiated with respect to P1, whatever we had differentiated with dou P loss with respect to P1, P2, P3, like that we are differentiating. Okay, so just like that, I am substituting this and taking it as equation number 1. So what I am doing is, I am substituting df1 divided by dp1 here, and dou p loss divided by dou p1 here. So simply like that, I am substituting 7.92 plus 0.00314 p1, that is equal to lambda into 1 minus 0.0006 p1. Okay, so take this as equation number 1. So after decimal, whatever the values it is coming, that you have to clearly mention over here. While doing calculation only, you have to round off to 4 digits. Like after decimal, 4 digits you have to round off. Otherwise, don't round off anywhere. Okay. while doing calculation only, you have to round off up to 4 digits. Here and all, don't round off. Whatever the value that is being given, or whatever the answer that is you're getting, same answer you have to keep it over here. Otherwise, the tolerance limit will goes very high. Say for example, demand is 850 megawatt, it may come around 847 megawatt. Okay, 3 megawatt deficit it will come. So 3 megawatt means it is very it is very more. 3 megawatt, that is 3 into 10 to the power of 6 watts. It's very more. So that you need to take care. Take care with. Okay, similarly for all the generating units, we are substituting, that is 7.85 plus 0.00388 P2, that is equal to lambda into 1 minus 0.00018 P2. Take this as equation 2. Similarly, you solve in your note. You solve in your notebook. Okay. Next, from the third generating units. So if you substitute, you will get the equation like this. So you take this as equation 1, 2, and 3. You take this as equation 1, 2, and 3. And if you see, like, these equations are very complex. These equations are very complex. Why? Because you can also solve. The thing is that it will take more steps. It will take more steps to solve. And also, if you see, like here also, P1 is there. If you really solve this 3 equation, so like the solving, like it will take more steps. Okay, more steps, very complex to solve, and hence what we are doing is we are randomly assuming the values for P1, P2, and P3. Randomly assuming the values for P1 and P2 and P3. So what is the total demand we have seen in the problem? We have seen in the problem total demand as 850 megawatt. So with that, within that 850 megawatt, what we are going to do is we are assuming certain values for P1 and P2 and P3. We are assuming certain values for P1, P2, and P3. Okay. So you can also take any values. I am taking like P1 as 400 megawatt, P2 as 300 megawatt, P3 as 150 megawatt. So it is not mandatory, like you should also take 400 megawatt, 300, and 150 like that. You can also take like 500 megawatt, then some 100 megawatt, then again 250, like that. It has to satisfy the demand. It has to satisfy the demand. Otherwise, you can take any values. But in practical, how these values they are assuming, in the sense, depends on the installed capacity of the generating units. If you take like the practical system, the practical generating unit, the installed capacity of the generating units might be there. Say for example, if you take the thermal generating units, total installed capacity is 4,500 megawatt. Stage 1, say for example, stage 1, 1,000 megawatt. Stage 2, 1,500 megawatt. Stage 3, 500 megawatt. Like that, many stages might be there. Depends on the demand. What they will do is they will increase the generation or they will decrease the generation, whichever the, say for example, the demand is 1,500 megawatt for that particular thermal generating unit, means they will on 1,500 megawatt. If the demand is suddenly dropping for an half an hour or 1 hour like that to 500 megawatt, means they will slowly shut off the 1,000 megawatt. Then they will simply start this 500 megawatt. Or otherwise, the demand is increasing like anything, like it is increasing like another 1,000 megawatt. Like 1,500 megawatt is already running, means again they will start another 1,000 megawatt. Like that, they may increase. So with the installed capacity of the plant, you can easily consider this value. It is not mandatory, like you can assume random values for like this is an example problem. That's why we are considering some values, some certain values. Sometimes in the problem itself may be given. In the problem itself may be given the installed capacity of the generating unit. 1 might be of 1,000 megawatt, 2 of 500 megawatt, 3 of some 300 megawatt. Like that, they might be giving. If it is not giving, we can consider. In practical case, I already said from the installed capacity of the generating units, we can easily assume these values. But ensure that it should satisfy the power demand. it should satisfy the power demand. That is whatever the power demand is given in the problem. So what is the power demand is given in the problem? That is 850 megawatt. So we have to check like the satisfying the 850 megawatt like that. That's all. Next. So we have assumed certain values. So what we are doing is we are substituting P1 is equal to 400 megawatt, P2 is equal to 300 megawatt, and P3 is equal to 150 megawatt in the right hand side of the equation number 1, 2, and 3. And further we are proceeding the problem. And also once we have calculated like P1, P2, and P3, what we are going to do is we are calculating the losses also, because the PLoss PLoss function already given. Function is already given in the problem, from the problem. So what we are doing is from the assumed value, we are going to find out the losses also. Definitely certain losses might be there. So what your generation transmission corporation, how they are claiming, like state transmission corporation, or it is a national transmission corporation, or local like district transmission corporation, it might be differing. In India, only state transmission corporation is available. Whereas if you take some foreign countries, the area wise, like a city wise transmission company is available. Like that, many things are there that we'll see in the separate class. Okay, so here depends so definitely your transmission companies will claim the losses like 18%, 15%, 12%, 10% like that. So recently they told like we have reached up to 12% losses. Definitely losses might be there. If there is no losses means the ideal system you can't as we did it in the previous problem, how we solve without losses, we solve. No, we can solve in the problem, example problems we can solve, but in practical generate scenario, definitely losses might be there. Definitely at least 15% losses might be there, to the maximum of 20%. It may decrease up to 12% or 15 to 10% like that. So that losses we are going to find out here. So from that loss equation, what we are doing is we are substituting the considered value and we are finding out the PLoss. So if we finding out the PLoss means it is coming around substituting the values here for 400, 300, and 150. Here we are getting like 15.6 megawatt. Always unit, write the units. Whenever you're solving the problem, don't forget that units. Even though if I forget something in notes also, you don't forget. Okay, units always, what you have to do is you have to just write the units while solving itself. Don't think like after solving the problem, we can write the units. Sometimes you will forget, and definitely you might be losing the problems. Why? Because why I am insisting on units in the sense, if you're not writing units, this problem, say for example, you are finding out the PLoss as 15.6 mega, instead of 15.6 megawatt, you're just writing 15.6. Okay, that 15.6 might be of, you didn't mention any units over that. That might be of watts or kilowatts, megawatt. That is some difference between watts and megawatt. How much? 10 to the power of 6. Okay, so say for example, the previous example I told, no, instead of giving 15, say for example, I need to give you like 15 lakhs. Say for example, I borrowed 15 lakhs. I need to give you 15 lakhs to you. Okay, instead of giving 15 lakhs, I'm giving only 15 rupees. Whether you accept? No, no one will accept. Okay, so like that, in similar way. So this is also very, very important. This watt, like a megawatt. Okay, so whatever. So in the power generating units, we are always any power generating units. It will be always okay, mentioned in megawatt only. 1000 megawatt, 5500 megawatt. Like that, it should be always mentioned in megawatt only. So units are very, very important. So we have found out this PLoss. Now what we are doing is we are substituting that is P1 as 400 megawatt, because we already considered, no, we are substituting P1 as 400 megawatt in the right hand side of the equation, the right hand side of the equation number 1. So if you substitute the 400 megawatt in the right hand side of the equation number 1, so you will get the equation like this. So in this you may get a question, sir, why can't we solve substitute the all for the left hand side also? Like if you do like that also, but the thing is that we consider some generating units. We consider like this might be of some 400, some 300 like that. So we need some answers for that. We need some answers for this. Simply like that, you can do now. It will become like a lambda, lambda, lambda like that. 3 lambda is come. Then 3 different lambda. Then it might be like a, you can also solve, but it might be the solution might be of vary. Your exact solution might be of varying. So what we are doing is we are substituting in the right hand side of the equation alone, and further we are proceeding. Okay, so we are taking this as equation number 4. Similarly, from equation number 2, we already know, like differentiated, no, sorry, that formulated, no, equation number 2. So from that formulation, what we are doing is we are substituting P2 is equal to 300 megawatt. So here you write substituting 300 megawatt in right hand side of the equation number 2, like that. So what we are doing is we are substituting and finding out the answers, further simplifying and finding out the answer. Take this as equation number 5. Okay, simple, your scientific calculator will all do this things. Next, from the equation number 3, what is the equation number 3? 7.97 plus 0.00964 P3, that is equal to lambda into 1 minus 0.0024 into 150. Okay, so here what we are doing is we are substituting P3 as some 150, 150 megawatt. So P3 as 150 megawatt in right hand side of the equation number 3. Okay, right hand side of the equation number 3, and further simplify. So you'll get for this 3 equation 4, 5, and 6. So why we are going for this equation number? Now easy for understand. You can easily substitute. Otherwise, sometimes what you guys will do is, so after finding out some lambda, you don't know where to substitute. You will substitute in equation 1, 2, and 3. Again, that answer will not come. Again, you will feel confused, and again you will go to this equation again. Time consuming. It will eat our time. Okay, while solving our problem, while solving the problem, it will simply eat our time. Why? Because minimum it's like 25 minutes, maximum 25 to half an hour. After half an hour is the maximum time for solving the problem. Okay, so if you know all this formulation, if you're fast with the calculation, easily you can complete within 15 minutes also. Like if you're very confident and your hands will be might be playing in your calculator, now you can easily solve this problem. Okay, but while substituting and taking out, we have to very if you miss after decimal 1 digit or something, a round off something like that, then tolerance limit you'll get 8%, 9%, like 10% also. So only 0.5% only allowed, as I already said. Okay, say for example, your power demand is 850 megawatt now. 849.5 and above is acceptable. 849.5 and above is acceptable. 849.9 means very good. 849.996 or is 99, that is very good. But due to some rounding off, you will get 849 some above 5 is good. 0.5% tolerance is good. Why? Because we are rounding. Otherwise, you'll lose the marks depending on the thing and whatever the mistakes you did. Only step mark only will be given, like 1 or 2 marks only will be given for this particular problem. So next, what we are doing is, we know like generation, the power balance equation of economic load dispatch with considering losses. That is generation that equals to demand plus losses. Whereas in without losses, generation is equal to demand. So here generation is equal to demand plus losses. So what is generation? That is generation is nothing but whatever the generation that is happening in the unit 1, 2, and 3. So if you take like a P1, P2, and P3. Okay, like power generating from first generating unit, second generating, third generating. So P1 plus P2 plus P3 is equal to demand plus losses. So what is the demand is given in the problem? Demand is 850 megawatt already given in the problem. So just substitute it. PLoss, that is power losses, already we found out. Already previously we found out that also you substitute here. So 15.6 megawatt. So further calculating, that is 865.6 megawatt. That is P1 plus P2 plus P3 is equal to 865.6 megawatt. Take this as equation number 7. So many people loss problem, what they will do, the blunder mistake is they will not add loss over here. Why? Because the previous problem what we did, like generation is equal to demand, that is P1 plus P2 plus P3 is equal to demand. Simply like that, what they will do is they will calculate P1 plus P2 plus P3 is equal to demand, like 850 megawatt. Simply like that they will take, and they will further they will proceed, and the answer also will come different answer. At last it will not satisfy the demand, it will go beyond the demand, or otherwise it will go comes very minimum to the demand. Like tolerance percentage is say for example, instead of 850, like you will get 840, something like that. Less values also, like more values also, sometimes 855 megawatt you will come. 855 megawatt, how it will come? Because generation itself is less and loss is also there. Then some instead of I'm telling you some example, so that also sometimes the mistakes will do. So what loss problem is asked now, always you should add the losses over here. Next, from equation number 4. From equation number 4, we are taking this P1 outside. So that is, if you take the P1 outside, that is P1 is equal to 0.976 lambda minus 7.92 divided by 0.0031. Like that, similarly, we are taking out P1, P2, and P3 outside. Okay, here P1 we are taking outside, here P2 we are taking outside, here P3 we are taking outside. So what we are doing is we are substituting in this equation 7. Okay, there from equation 4 we are taking out P1. From equation 5 we are taking out P2. Then from equation 6 we are taking out P3. Okay, so take this as equation 8, 9, 10. Then substitute 8, 9, 10 in equation number 7. Substitute P1, P2, and P3 in equation number 7. Okay, so further what we are doing is we are substituting and further simplifying. Like that is 865 megawatt. I think here I made a mistake. So 865 megawatt. Okay, 15 megawatts are there. So I have written like 856, 816 megawatt. So further, if you are calculating, further simplifying, you have to take the lambda outside, and you have to find out the lambda. You have to take down the lambda outside, and further you have to take down the lambda. So here, if you simplify, you will get some answers, and further simplifying, you'll get lambda is equal to 9.525. So simply your scientific calculator will do all these things, and while taking the values and typing in within the scientific calculator, you should be very careful. Without the mistake, you should do. Okay. So next, now you'll get the lambda value. Next, what you have to do is we have to substitute lambda is equal to whatever the value, that is 9.525 in equation 8, 9, 10, because P1, P2, P3 for finding out P1, P2, and P3. So further finding out 8, 9, substituting in 8, 9, 10, you'll get like P1 value as 440.58 megawatt, P2 is equal to 299.13 megawatt, P3 is equal to some to 125.73 megawatt. Around this value, you will also get. Okay, so you find out exactly. Sometimes in the problem, I'll be rounding off, like after decimal, I'll be rounding off. So you don't round off, you take 4 values after decimal, 4 digits, then you'll get exact answer. So after that, you'll get the like power generating unit unit from the power generation from unit 1, that is P1 is equal to 440.58 megawatt. Power generation from unit 2, 299.13 megawatt. Power generating from unit 3, 125.73 megawatt. So these values you will get at the last. So the problem is not at stop, not at stopped. Why? Because we have considered previously. You have to go to previous. What we did is we have considered the values. We have considered the values as, yeah, we have assumed the values as P1 is equal to 400 megawatt, P2 is equal to 300 megawatt, P3 is equal to some 150 megawatt. But we don't know whether this is the only answer will come or not. We don't know. By assuming these values, we found out some P1 and P2 and P3. We found out the power generation from unit number 1, 2, and 3. That is P1 is equal to 440 megawatt, then 299 megawatt, 125 megawatt. We found out. Okay, so now we'll get some. This is the first iteration. What we did is that from that assumed value, the first iteration starts. Okay, right from there, first iteration. So in that first iteration, we got some values like 440 points or something values we got. But if you see like P1, P2, and P3 are quite different from the starting values, and we have to go to the second iteration, and further we have to continue whether the considered value is correct or not. Whether if you get with the say for example 3 iteration you need to do. First iteration we have completed. So what you have to do is by taking this value as 440 megawatt, like 299 and 150 megawatt here. So you have to come to this step where we, yeah. So now the 440 megawatt, 299 megawatt, some 125 megawatt, like that the answers we got now. That thing we have to substitute. This is the iteration number 1 from the previous. So this is the so after we are taking like 399 megawatt, some 299 megawatt, like that we got now. That answer you have to substitute here. That this is iteration number 2. Again we have to proceed. Like so. With this, what we have to proceed like we have to find out the PLoss. Again further we have to substitute the P1 is equal to whatever the values we got in first iteration. That is in the equation right hand side of the equation number 4. Again from the right hand side of the equation number 5. Right hand side of the equation, P2 in the right hand side of the equation number 5, and P3 in the right hand side of the equation number 6. Like that we have to substitute. Again further we have some losses. We say for example here 15.6 megawatt. So while doing, you'll get some 20 megawatt. Say for example, I'm telling in the second iteration you are getting 20 megawatt. So again what you have to do is you have to add the loss over here, and whatever the demand that you found out from that by adding, like you will get some values, no. So this, that values you have to add over here. Again, further you have to proceed. P1 plus P2 is equal to some megawatt you will get now. That again you have to from this equation. Again you have to P1, P2, P3. Again you have to substitute in this equation number 7. Again what you have to do is you have to find out the lambda. Further simplification, you will be easily find out the lambda. Say for example, you will get lambda is equal to some 10.5 like that. For example, I'm telling you will get some values, some 10.5 something like that. Again, you need to substitute that is in P1, P2, and P3. Again, you will get some values. Say for example, after the second iteration, you are getting like 442 megawatt. P2 is equal to 300 megawatt. P3 is equal to 127 megawatt. Like that you are getting. For example, I am telling that is not an exact answer. If you are getting the values near to that, near to that value. Say for example, 3 iterations I said. Now similarly, you have to solve with the 3 iteration. If you are getting the same values, like say for example, that values is not changing that much. Okay, then whatever the considered values is correct. Okay, you can stop the iteration and you can take that whatever the answer by the end of the third iteration you will get whatever the answer. You can directly go for the this is the solution, like that you can go for. If you add that also, you'll get approximately, say for example, with the losses, you'll get approximate answer, not a perfect answer, approximately. So say for example, 865 like that, you'll get some near to that 864 for a point something you will get. Okay, so if you do like that, okay, you can simply stop. You can simply stop, or otherwise, if you are not, it is deviating. Say for example, if it is deviating heavily, like instead of 400, instead of 440 megawatt, it is coming like 470 megawatt. Instead of 300 megawatt, it is coming like 350 megawatt. Instead of 125 megawatt, it is coming like 100 megawatt. So the deviation is very more. In that scenario, what you have to do is, you have to consider the same values again. Again, you have to repeat that iteration. Understood? No, repeat that iteration again. So whenever the you get nearby values, when comparing from the first iteration, second iteration, third iteration, whenever you are getting not varying that much, okay, not varying that much, then because if you consider, if you take this value, it is deviating more. Why? Because we consider 400 megawatt here to 300 megawatt here 150 megawatt. It is deviating more. That is, it is coming like instead of 400, it is coming like 440 megawatt. Instead of 300, this is okay. Second generating, so okay. Third generating 150, instead of 150, you are getting 125. This is more. But say for example, second iteration also you are getting near to these values, then you can stop. Understood? No. So whenever the values you are getting near to that values, not much deviation is coming, then you can stop that iteration and you can conclude in that scenario. Say for example, in the exam, if this similar kind of problem is asked, what you guys should do is, you can stop up to 2 iteration. No need of going for 3 iteration because it is time consuming. Okay, so you have to solve somewhat fast, and also 2 iteration you can stop. With 2 iteration you can conclude. Why? Because for time consuming sake, for exam check. But real time, if you want to do real time, if you want to find out exact value, then we have to go for 5 iteration, 6 iteration, 10 iteration, 100 iteration also. But in the paper and pen, we can't we can't able to solve 100 iteration. Why? Because might be very time consuming. So for 1 iteration itself, minimum it is taking 10 to 15 minutes. Minimum 10 minutes for 1 iteration. So 2 iteration means maximum you can complete within 25 to half an hour. So if it is going more than that, say for example 5 iteration, if you go for now, again it will take 1 hour like. So don't in exam stop up to 2 iteration. And conclusion, clearly you have to write conclusion. After this, in the conclusion, since P1 and P2 and P3 are quite different from the starting values, again we are further going to the proceeding to the second iteration for verifying the answer. Like that, the conclusion you need to write. Again, what you have to do is, you have to go for the next iteration. Again, you have to solve. Again, that conclusion you have to write. So at the end of in exam, at the end of second iteration, you have to write the conclusion clearly. So this is not varying that much. So the final values of power generation from the P1 and P2 and P3 is this one, by considering the values as some values, whatever you consider for that value. So like that, you can write the conclusion clearly. You have to highlight the answer. Okay, then only you'll get full marks. And don't stop up to 1 iteration, because this kind of PLoss problem, don't stop up to 1 iteration. You have to further proceed to 2 iteration. Then only, if you stop up to 1 iteration, then only half marks. That is, even for 10 marks, only 5 to 6 marks only will be given. So if you go for 2 iteration, then whole marks, you will get full marks. But the one condition is that don't do any careless mistakes. Decimal, then while taking and writing, and while typing in the calculator also, you might be doing the mistakes. So you have to very careful, concentrate, and you have to do the problem. Then you'll get the perfect answer.